All right, this one's in kind of a weird form, the denominator here, so let's just make it look a little bit easier to deal with. N equals 1 to infinity, negative 1 to the n plus 1. This is n to the 3 halves. So if I plug in 1, I have my middle finger awkward. If I plug in 1 here, I get 1 over 1 to the 3 halves. Plus I plug in 2, I get negative 1, and this is 2 to the 3 halves. If I plug in 3, I get 1 over 3 to the 3 halves minus dot 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 dot. Feels very alternating series. Let's check the limit as n goes to infinity. The limit as n goes to infinity of 1 over n to the 3 halves. Note that this is not a L'Hopital's rule candidate. Really no need to multiply top and bottom by 1 over n to the 3 halves, because if you do that, you'll just get right back to the original expression I have here. As n goes to infinity, my denominator gets very large. 1 over a large number is 0, so that's a check. Is it decreasing? Let's just do the easy decreasing here. So this is decreasing. Is n plus 1 bigger than n? Yes. Let's take the 3 halves of both sides. My inequality is maintained. Again, the only time my inequality changes is if I multiply by -1 or take the reciprocal of both sides. Here I'm going to take the reciprocal of both sides. That's a 3 halves, sorry. So therefore decreasing. That's a check. Prove divergence or convergence. Well, this is a p-series, right, without the -1. 1 over n to the 3 halves, n equals 1 to infinity, is a convergent. P equals 3 halves, which is bigger than 1. P-series. And then so the last thing is, since it's convergent, and it's an alternating series, we say absolutely convergent because we don't need the positive and negativeness to make this thing converge. So this is absolutely convergent alternating series test.